Okay, so for 1D elastic collisions, we have two masses moving along a 1D line. So if I label the axis as rightward positive, then if their initial velocities are UA and UB, right? So moving to the right, UB, U and UB, taking rightward to be positive direction for the vectors. Then after the colliding, let their final velocities be VA and VB. So once again, same axis, but after colliding, VA and VB. So usually we use U to denote the initial velocities before the collision, and V to denote the velocities after the collision. Then conservation of momentum, linear momentum, tells me that the momentum before and after stays the same. So the momentum before, right, in the first scenario, the momentum before would just be mass of A times the velocity of A plus mass of B times the velocity of B, right? And the scenario after would be same thing, just that we replace the U's with the V's. So equation 67 is the conservation of momentum. And equation 68 is the conservation of energy. So for 1D elastic collisions, right, elastic means that their total kinetic energies are conserved. So half MUA squared plus half MBUB squared equals to half MAVA squared plus half MBVB squared. Right? Okay, so with these two equations, we're ready to solve them. So the reason why we're already ready to solve them is because UA and UB are known quantities, right? The question will give you UA and UB. They will give you the initial velocities. Then the question will ask you for VA and VB. They'll ask you for VA and VB. And in this case, these two are unknowns. So we have two unknowns and we have two equations. And generally, the rule of thumb is that whenever you have n unknowns and n equations, you can generally solve for the n unknowns. So we have enough information, we have enough equations to solve for the final velocities. Okay, so how do we solve it? One can realize that we can perform the following trick. So if we take the conservation of momentum equation and rearrange it, right? So we move it such that the MA terms are on the left side and MB terms on the right side. Then we get the following equation 69. Then likewise, if I rearrange the energy equation, right, you can see that I can bring this term over. So I have the half MA factorizes out. So let me just do it over here. So half MA factorizes out. So half MA UA squared minus VA squared, right? And likewise, if we bring this guy to the right hand side, then half MB VB squared minus UB squared. Okay, so if I see that this is a difference of two squares, I can write it as UA minus VA times UA plus VA, right? And likewise for this, then I arrive at equation 70. So something nice we see over here is that equation 70 is a multiple of equation 69, right? Specifically, we see that this factor is precisely this thing, and this factor is precisely this thing. Okay, so if we divide equation 70 by equation 69, then we get that UA plus VA equals to UB plus VB. So this, if we rearrange it a little bit, and I'll tell you why we want to rearrange it as such, right? So right now it may seem a bit confusing. There's U, there's V, and then there's A, and then there's B, and then it's flying all over the place. But just hang in there a little bit, right? If you just follow along, you'll realize that there's a nice interpretation for equation 72. So remember previously that I said that if I think of it as a line, right, and the velocities are UA and UB moving rightward, right? Taking rightward as positive, then we can think of UA minus UB as how fast the distance between the two objects, right, MA and MB, how fast the distance between the separation between the two objects is closing down. So what I mean by that is that if the initial velocities were such that UB is bigger than UA, so imagine if UB was a large vector, right? Then actually mass B is moving farther and further away from mass A, right? So they will actually never collide. So if the collision happens, that would imply that UA is bigger than UB. So only if UA is, if and only if UA is bigger than UB, right, then the collision happens. Because if UA is bigger than UB, suppose UA is a huge vector and UB is maybe moving very slowly, it could even be moving in the left direction, right? That'd be considered negative. Then the distance between them is closing down. The MA is catching up with MB, right? Mass A is catching up with mass B. And so if UA is bigger, if the A's velocity is larger than B's velocity, then UA minus UB, right? The difference in the velocities will be how fast the two objects are approaching each other. Okay. Yeah, and likewise, if we think of the same scenario but for after the collision, right? So after the collision, you have your masses MA and MB, but they're moving at velocities VA and VB. It's because V stands for the final velocity. So VA and VB. Then because their velocities only change during the collision, right? The velocities after the collision must be constant. So that will mean that that will mean that the velocity of B after the collision must be faster than the velocity of A after the collision. Because if that wasn't the case, then they're gonna collide again and again and again. So, and we can also see from this conservation, from this equation 72 over here, that if UA larger than UB, if this side is greater than 0, then the right hand side is also greater than 0. So because there's a minus sign here, that will imply that VA minus VB is less than 0. Okay, and hence VA is less than VB. And if we interpret that, then if we take the difference of the velocities, then we realize that that's just the rate of the velocity, or rather the rate of separation for the two objects. So they often say velocity of approach and velocity of separation. Personally, I prefer to say rate of approach and rate of separation, or speed of approach and speed of separation, because velocity itself, I'm just nitpicking, but velocity itself has a notion that it can have negative velocity, and I do not really want to think about what it means to have a negative velocity of approach, right? Both of these quantities are greater than 0, right? They're equal and greater than 0, but I do not really want to think of what it might mean if they're less than 0, right? Then they're not really approaching each other anymore, aren't they? So I prefer to think of it, the word velocity here is commonly used, but I prefer to think of it as a speed or rate, right? Rate of separation and rate of approach. That's, to me, is clearer. Okay, so yeah, so over here I just basically elaborated what I said above, and so with equation 72, and we'll see soon, right? We'll see soon that equation 72 can be derived using the center of momentum frame also, right? And it leads to actually a very elegant picture later on. But for now, right, we have derived equation 72 by taking the two conservation equations, right? One for momentum, one for energy, and dividing one by another, right? So with our equation 72, and we can use equation 72, right? We can use equation 72 because now, if we take a look at what equation 72 is implying, is saying that VA, right? We have VA now in terms, linearly in terms of VB, right? So the whole idea is that previously we look at the equation here. Previously, the momentum equation is a linear equation, whereas the energy equation is a quadratic equation, right? And quadratic equations are harder to solve than linear equations. But by doing some manipulation, right, essentially we have arrived at a linear equation relating, we've transformed, right? We've transformed the quadratic equation here, we divide it by the linear, so we get a linear equation that we can use to solve simultaneously with the momentum equation, right? So basically the rate of approach equals to rate of separation equation is a rehashing, is a rephrasing of the conservation of energy equation, right? From quadratic to linear. So now we have two linear equations, and that is much easier to solve. So all that's left to do is to rearrange equation 72 into so now we have two linear equations instead of one linear, one quadratic, right? And the rest is easy to solve because linear equations are easy. So we just rearrange equation 74 into the following and substitute back into equation 73, and then we get the following solution for VB. Okay, and likewise, if we do we continue, then we can get a solution for VA. Okay, so now we have fully solved for VA and VB in terms of the initial velocities UA and UB as well as the ratio of the masses. Okay, so personally, this looks a bit messy, right? There's a factor of 2m here, mb minus ma, and so on. Do you need to memorize this? Personally, I have never memorized this before, so what I personally do is I just derive it on the spot, and I find that it's clearer, and I personally prefer deriving it than memorizing it. But if you feel like it's gonna take a lot of time, then you can feel free to memorize it. Yeah, I'm just not so much of a memory type of person. Okay, so so let's move on to an example question.